MBA633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this clip, we will continue our discussion of probability by focusing on conditional probabilities and the independence of events. Sometimes we are interested in the probability of an event given that another event has occurred. An example would be computing the probability that a train arrives on time given that it has left on time. In other words, I'm telling you that one event has happened for certain. In other words, it has left on time, and I'm asking you to compute the probability that the train would arrive on time. And there are lots of other examples. You can see three others over here. Probability that a PC crashes given that a particular operating system is installed, and so forth. Or probability that a website is visited given its number of in-links. The higher the number of in-links, the higher the likelihood you would think that a website is visited. So let's look at a specific example about how you would go about computing conditional probabilities. You run a small business that produces plastic panels for use in home building, and periodically you test them for scratch and shock resistance. So let's say a set of 150 panels were tested, and this is the pattern that emerged. So you can see that in this experiment there are 150 outcomes. Each outcome is a pair of values, the pair representing the shock resistance and the scratch resistance. So let's look at this grid and pick a number. The 125 that you see on the grid over here, 125 means that out of the 150 there are 125 panels that tested high for shock resistance and high for scratch resistance. Okay, so let's say we pick a panel at random and we define E as the event. By the way, we defined what an event is in a previous clip. So an event is simply consists of a set of outcomes that meets a certain condition. So we pick a panel at random and let's define the event E as being the event that the panel has high shock resistance, and F is the event that the panel has high scratch resistance. So what is the probability of E? The number of outcomes in the event E, that it has high shock resistance, is simply 125 plus 7. And since there are 150 outcomes in the sample space, the probability is simply 125 plus 7 divided by 150, or 132 divided by 150. Similarly, the probability of F, that the panel would have a high scratch resistance, the probability is simply 125 plus 12 divided by 150, right? Because that's 125 plus 12. Those are the panels that tested high for scratch resistance. The probability of E and F, you remember this definition in a previous clip. This consists of the set of outcomes that are both in E and in F. And we know from this grid that there are 125 such panels. So the probability is 125 divided by 150. And notice that all these three probabilities that we just calculated, the denominator is 150 because there are 150 outcomes in the sample space. That is the set of all possible outcomes. Now, what if I tell you that this panel that I picked, I'm telling you that it has high scratch resistance. In other words, the event F is given to you. It has happened for certain. This panel that I picked has high scratch resistance for sure. Given that information, what is the probability that the panel also has a high shock resistance? What is the probability of E given F? Now, as soon as I'm telling you that we're talking about F, that is, the panel has high scratch resistance, I know from my grid that I'm talking about 137 outcomes, not 150, because 125 plus 12, that's what we have over here. So out of those 137, the number of outcomes that are also high shock resistance, that is the event E, is 125. So you see this symbol over here, the notation that we have here. The way you read it is the probability of E given F. Okay, and the number that we come up with is 125 divided by 137. And the reason we did it this way is so that you can see that the very concept of conditional probability is that you restrain or constrain the sample space to the set of outcomes that define the event that is given. the event that is given and you know that has happened for sure, the number of outcomes in that event now becomes the sample space. Okay. Now I'm going to take this 125 over 137 and rewrite it in a slightly different way. What I'm going to do is I'm going to write it as 125 divided by 150, and the denominator I'm going to write it as 137 divided by 150. I haven't really changed anything by doing that, right? Why have I done it this way? Because you can see that 125 divided by 150 is this fellow, and 137 divided by 150 is this fellow, isn't it? Therefore, using the notation that we already have, P of E given F is equal to P of E and F divided by P of F. Okay. In other words, the conditional probability of E given F is equal to the joint probability of E and F divided by the probability of F. Okay. So now, when do we say that two events are independent? Let's take these two events E and F. We would say that they are independent if probability of E given F is the same as the probability of E. In other words, knowing whether or not F has occurred tells me nothing more. Okay, and I could state it the other way as well. Also, P of F given E is equal to P of F. Okay. If either of these two conditions hold, then we say that events E and F are independent. Now you can do the calculations and see whether in fact E and F are independent. I think you will find that they are not. But if we take these two relationships as the definition for independence, okay, then we can plug them back in here. In other words, if P of E given F is really equal to P of E for independent events, then here's what the equation becomes. I get P of E and F divided by P of F is equal to P of E. Correct? In other words, P of E and F is equal to P of E times P of F. Okay, so this is the very famous multiplicative law. Okay, so what does the multiplicative law say? It says that if two events E and F are independent, okay, if these two are independent, if events E and F are independent, then their joint probability, the probability of E and F, the two of them happening together, is simply the probability of E multiplied by the probability of F. So remember that to find the joint probability of E and F, you can multiply the probabilities only when the two events are independent. So this is the famous multiplicative law of probability for independent events. So two events are independent, E and F are independent, if the conditional probability is the same as the unconditional probability. Okay, now just for practice, I'm going to just state another problem here. A family has two children, not twins. What is the probability that the younger child is a girl, given that at least one of the children is a girl? Assume that boys and girls are equally likely to be born. See if you can come up with the answer. The answer is 2/3, and see if you can come up with the logic that will yield the value 2/3 based on the discussion that we just had in the previous slide. So this is a discussion of conditional probability, and it's very useful in testing whether two events are related or not. Just by the way, remember that two events being independent is very different from saying that they are mutually exclusive. In fact, if you have two events E and F and they are mutually exclusive, they are extremely dependent because what you're saying is that if one event happens, the other cannot happen. E and F are mutually exclusive. If one happens, the other cannot happen. In other words, the two of them cannot happen simultaneously. All right. So now if you look at our definition of conditional probability, okay, you look at the numerator, you see it's the joint probability of E and F. All right. So in order for two events to be independent, there must be a non-zero probability that they can occur together. So independent events and mutually exclusive events are completely different, you know, and mutually exclusive events in fact are highly dependent events. Okay, so tests for independence. How would you test if two events are independent? You would test if this relationship holds or this relationship holds. Either one of them is saying the same thing, is the same test, and you can test if two events are independent. In other words, knowing one tells you nothing about the others occurring